So we've looked at this new idea of entropy, but maybe you're struggling to kind of visualize how this fits into things like chemical reactions. So that's what we're going to look at now. All chemists in general are interested in is the entropy change of reaction. In other words, if the entropy increases or entropy decreases in a reaction, because that informs us about whether a reaction is going to be feasible or not. One way of working out the entropy change in reaction is just to straightforwardly calculate it using your calculator, and we'll look at that in a couple of pages' time, because entropy values you can just look up on the table. Entropy is measured in this unusual unit, joule per Kelvin per mole, but it's just in the table. And you just calculate the entropy of your reactants, your entropy of your products, find the difference, that'll give you the entropy change. If your entropy change increases, it's got a positive delta S value. If it decreases, it's got a negative delta S value. So we'll look at that in time. It is sometimes possible to work out an entropy change roughly just by looking at the layout of a reaction without actually doing any calculations. In order for you to do that, predicting entropy changes, you need to have a wee bit of an appreciation about what kind of entropy is associated with different types of substances. And generally all it comes down to is what state they are. One very useful table is given here. So this is actual entropy values given for water in its three states. So ice, water and steam there. Hopefully you can see the trend there. The lowest entropy of water is when it's frozen as ice. Next is liquid water, and the highest entropy is associated with a gaseous water, steam. And hopefully it's not too hard for you to maybe grasp why that is. If you sort of analyse how particles are arranged in solids, liquids and gases, this is going right back to what you did in year 8. In solids, obviously they're lined up in neat rows, they're all kind of touching each other. In liquids, they're still touching, but they're no longer neatly aligned, they're kind of tumbling over each other. But in gas, they're all separated and moving independently. That is showing an increase in disorder. In a solid, you're very ordered. Particles are in very prescribed locations. Yes, they're vibrating, which gives them some entropy, but in general they are quite ordered. And that gives it quite a low entropy value of 48 there for frozen water. When you melt a solid into liquid, you got a lot more disorder because these particles are now free to move. They're not completely free to move. They have to stay touching each other. They have to stay at the bottom of their beaker or vessel, but they have a lot more freedom and disorder with how they move, and therefore the entropy increases. The highest entropy state of a substance is always going to be that substance is a gas, because in this case all the particles are acting independent of each other. There's lots of ways they can arrange themselves, therefore there's lots of disorder in the system, and you see this very high value for steam here of 189. So it says here, the general trend shown in the table is the entropy of gases tends to be higher than entropy of liquids, which in turn higher than entropy of solids. So even without using any numbers or any sums, that rule will always kind of hold true, and we can use that to kind of analyse some reactions, as we'll see in a second. One we note there, we've mentioned before, notice that they're all positive values, so we don't actually need any plus or minus signs in these entropy tables, though we will when we're describing changes in entropy, as we'll see in a second. Just building on that a wee bit, just on a little kind of graph version, rather than looking just a table, this is kind of the same kind of stuff expressed as a graph. Entropy generally does increase as temperature increases, simply because vibrations are increasing, movements increasing, that's always going to increase disorder. So we see increase from 0 degrees Kelvin up to the point where, this is still for water, where ice is going to melt, then it increases more, then it's going to boil, then the steam is going to increase in entropy as it heats up and the particles move quicker. You've got these strange kind of vertical sections, that's just corresponding to changes of state. Temperature can't actually increase past the boiling point or melting point until everything has melted or boiled. I mean, you know that'll be true if you boil some water in a saucepan. The water doesn't get more than 100 degrees C while it's still water. All the energy goes into changing that state. It gives you a large increase in entropy. And then once it's all turned into gas, it can increase in temperature again, causing that increase in entropy. The key fact there though, gases have more entropy than liquids, liquids have more entropy than solids. So how can we use that without actually using any sums? We see that here with some examples. All you have to do here is state and probably explain whether the following reactions show an increase or decrease in entropy. And the key thing for the style of question is to analyse your state symbols. The actual chemical substances don't matter that much. In this first reaction we start with a solid. It breaks apart to form a solid plus a gas. In terms of what we know, solids tend to have low entropy and gases tend to have a high entropy. So if we're changing something which got an inherently low entropy into two things, one of which has low entropy but one has a high energy, it's pretty safe to assume that we're going to increase entropy here because gases as a whole tend to have much, much higher entropies than any solids. So how we would answer that question, we would say we've got an increase in entropy because we've got a solid going to a solid plus a gas. We would explain that gases have a higher entropy, or have much higher entropy, than solids, as gases are more disordered. And that just shows off the fact that we know that entropy is about disorderment and gases are more disordered, which justifies this explanation. Second question here. Magnesium plus oxygen goes to magnesium oxide. Here we've got a solid and a gas combining together to make a solid. It's kind of the reverse of the first example. The gas stands out as having the highest disorder of anything in this reaction, but at the end you just reduce everything down to a solid with quite low entropy. We're pretty safe to assume here that we've got a decrease in entropy. So it decreases because you've got a solid and a gas turning into just a solid. And our justification is that solids have much lower entropy than gases. As solids are less disordered. Final example is a wee bit different. Everything's actually a gas here, which might seem a wee bit trickier. It's similar to how we approach questions with equilibrium just involving gases and pressure. We're going to count up the number of moles of gas on each side of the equation. On the left, we've got 4 total moles of gas. On the right, we've got 2 total moles of gas. We know that gases are very disordered, but the more gas particles you have in a certain container, the more disorder you're going to have because there's more combinations you can have for 4 moles of gas in a container than there are combinations for 2 moles of gas in a container. So if you're making more moles of gas in a reaction, you're always going to increase entropy. In this case, we're decreasing the moles of gas in a container, therefore we're decreasing entropy. So justification for that one is we've got a decrease in entropy. The reason being we've got 4 moles of gas in this equation turning into 2 moles of gas. There are fewer particles of gas on the right hand side. Therefore, the system is less disordered. So again, we're not using any sums here, and if this does come up with a question, they'll give you ones which are quite clear-cut, which you can just kind of assume without using any numbers. So you're checking for things like solids turning into gases, or numbers of gases turning into different numbers of gases to analyse the entropy in the reaction. So that's all well and good, but we are scientists. Sometimes we want cold hard numbers to guide our explanations. So it is very possible to calculate entropy changes. This is quite a common style of question. Luckily, it's really not the most complicated calculation you'll ever come across. It's pretty much adding and subtracting numbers from each other. So the accurate way to determine entropy changes is use entropy values just from data books and data tables for substances in a reaction. The overall entropy change is found using delta S, S for entropy, equals total entropy for the products minus total entropy for the reactants. And it's as simple as adding up entropy values, then subtracting them. So I'm going to go through these questions here. You might even want to pause the video and have a go yourself because it's not much more complicated than you might expect. You've given an equation here. You're given values for the entropy of those different things in the equation. And you're trying to add up the total entropy, then subtract the reactants from the products. Only thing to bear in mind is if you've got mole values or balancing numbers in the equation, you have to take that into account into your numbers as well. As we're quite familiar with calculating things like enthalpy changes, that still counts. So in this first example, let's look at our reactants first. So our entropy of our reactants equals, so my reactants are 2 SO2s. The entropy of SO2 is 248. So 2 times 248. And we've got 1 mole of oxygen, so I'm going to add 205 to that. Put that in my calculator, I come out with a value of 701 joules per Kelvin per mole. Should always put units in. My entropy of my products is just 2 moles of SO3. That value is given as 257 in the question. So 2 times 257 equals 514 joules per Kelvin per mole. To calculate the change in entropy, I just need to do entropy for my products minus entropy for the reactants. So it's going to be 514 minus 701 equals minus 187 joules per Kelvin per mole. You can sometimes do a wee bit of common sense check with these kind of questions. If I was to analyse this at the start, I've got 3 moles of a gas turning into 2 moles of a gas. As we looked at in the previous page, we would hope that would be a decrease in entropy because we got fewer moles of gas on the right side. That's backed up by our calculation. A negative sign implies that entropy is decreasing across the reaction. Slightly different style question here, because obviously that's not too complicated. You're just adding numbers. They can get you to work out a missing entropy value. So we've got another process here. It's giving us at the start that the entropy change for that reaction is plus 139 joules per Kelvin per mole. We're given the entropy values for all the missing, or 3 of the substances in the equation. We're asked to calculate the standard entropy of steam, so that's this H2O here. Don't treat it any differently, just have a missing value. So I'm going to start with entropy of my reactants. So my reactants are Fe2O3. Its entropy as a solid is quite low, it's 90. I've got 3 moles of hydrogen, so that's going to be 3 times 131. And that's all I've got, so it's going to come together to 483 joules per Kelvin per mole. Entropy of my products. So I've got 2 moles of Fe, again it's a solid, it's quite low, so it's going to be 2 times 27. And then here's my missing value, so I'm just going to put 3x for steam because there's 3 moles of it, but I don't know the value for the entropy of steam. So putting that together, it's going to be 54 plus 3x joules per Kelvin per mole. My total entropy change is just as before, so the entropy change is my reactants minus my products. My reactants is products minus reactants. So 54 plus 3x minus 483. But I know the answer already. The answer is plus 139. Sorry, the answer to that's dumb. Just need to do a wee bit of rearranging now. So I need to get 3x by itself. So I need to transfer the 483 over the other side and 54 to the other side. That gets me 3x equals 568. X, just need to divide that by 3. And that gets me a value to 3 significant figures of 189 joules per Kelvin per mole. So there's 2 styles of questions for calculating entropy changes or describing entropy changes. One is without any numbers. You're just analysing the state symbols of a reaction to work out if entropy should increase or decrease. Or you can get a question where they give you entropy values and you're comparing the entropy of the reactants to the entropy of the products.